12.5 Lesson 1 Arc Length. Our objective for today is you'll be able to find the arc length of a plane or a space curve described by a vector-valued function. You will remember that we've been working on the problem of arc length for some time now. If you have an arc that is described by a rectangular equation, how do you find the length of that arc? We looked at that problem in Chapter 7. And then we looked at the same problem where the curve was described by a set of parametric equations. And how do we find the length of that arc? And then we looked at the same problem where you have a curve described by a polar equation, and how do you find the length of that arc? So today we're looking at the same problem, but now our curve is described by a vector-valued function, and how do we find the length of the arc in that case? Suppose you have a plane curve described by a vector-valued function. That same plane curve can also be written as a set of parametric equations. Now, to make my real valued functions, the component functions, match, I will go ahead and change this to x is equal to x of t and y is equal to y of t, some function of t. Or I could likewise have it the other way around, where I will have the component functions be represented by f of t and g of t for my vector-valued function. In that case, my parametric equations will be x is equal to f of t and y is equal to g of t. But the point that I want to make is the same curve can be represented in either form. So if you want to look at the problem of finding arc length, the problem of finding arc length for an arc described by a vector-valued function is in fact the same problem as that of finding arc length for an arc described by a set of parametric equations. Let's take a look at what we learned in Chapter 10, Theorem 10.8, arc length in parametric form. If you have a smooth curve C given by x is equal to f of t and y is equal to g of t, such that the curve does not intersect itself on the interval from t is equal to a to t is equal to b, except possibly at the endpoints, then the arc length of the curve over the interval is given by this definite integral. The definite integral from a to b, where the integrand is the square root of the sum of the squares of the derivatives of your individual parametric equations. Now, if you take a look at how we do arc length for a curve described by a vector-valued function, we do it the same way. And of course, you have Theorem 12.6, arc length of a space curve. Now, if you just restrict your consideration to plane curves, then this theorem that you see here as 12.6 will just simply be arc length is equal to the definite integral from a to b, and you just have one fewer component. So you'll have, if I'm using f of t and g of t for my component functions, I'll have f prime of t squared plus g prime of t squared and we'll integrate with respect to t. So how do you find arc length of a space curve or a plane curve? You do it the same way we did it in Chapter 10. You find the arc length of a plane curve the same way as we did in Chapter 10. If C is a smooth curve given by R of t is equal to either f of t, I, g of t, j, or if you want to use different notation to represent the component functions, you can. On an interval from a to b, then the arc length of the curve on the interval is given by the same integration formula that we had for arc length in parametric form. This is just another way of writing the integrand. You would find the derivative of your vector-valued function that gives you your arc, and then find the magnitude of that derivative, and that would give you this integrand. Let's take a look at example 2, finding the arc length of a helix. So we have here, find the length of one turn of the helix given by r of t is equal to b times cosine of ti plus b times sine of tj plus the square root of 1 minus b squared tk. as shown in the figure. And before we look at the figure, I'd like for you to just consider what this curve might look like. This is a three-dimensional curve, a curve in space. So you can see that we have our x and y component functions, and we can write them here. X of t is equal to b times cosine t, and y of t is equal to b times sine t. And to simplify our notation, I'll just write x is equal to b times cosine t, and y is equal to b times sine t. And I can divide each side of my equation for x by b. I can divide each side of my equation for y by b. And I can square each of these two equations, and I'll get x squared over b squared is equal to cosine squared t. Y squared over b squared is equal to sine squared t. Of course, we have the Pythagorean identity, sine squared t plus cosine squared t. When you add, you get 1. So when I use that Pythagorean identity, I'm able to eliminate the parameter, and I will have x squared over b squared plus y squared over b squared is equal to 1. If I multiply both sides of the equation by b squared, I'm able to see that what I get is the standard equation for a circle centered at the origin with radius b. So what that means is, if you just look at the x and the y components of this three-dimensional function, if you ignore the third dimension and you just focus on the x and the y components, and you're looking at the xy plane from above it, what you will see is a circle centered at the origin with a radius of b. And if you extend that circle above the xy plane and below the xy plane, you will get a cylinder. And the circle would be one cross-section of the cylinder. And it is on this cylinder that you will have the helix, the space curve, because on that cylinder you will trace points on the cylinder according to the third parametric equation that we have, which is for z. So we have z of t is equal to the square root of 1 minus b squared t. And for a particular value of t, you're going to get an x coordinate and a y coordinate, which will be somewhere on that cylinder. But where on the cylinder? Where on the cylinder is determined by the z coordinate, if it's going to be above the xy plane or below the xy plane, depending on the value of t. So when we look at just the x and the y component functions, we can evaluate each of the two functions at these chosen values of the parameter t, and we will get the output values that you will see now. And putting those together, you're going to get ordered pairs that are b0 corresponding to t is equal to 0, b is for x, and 0 is for y. So I'm putting things together now, so I should really have a boundary here. And then you're going to have, for t is equal to pi over 2, 0b. And then for t is equal to pi, you'll have negative b, 0, and so on. And if you plot these 5 points, you'll get the circle in the xy plane. And you can see here in the three-dimensional curve that's represented in 2 dimensions. Here we have the x-axis, here we have the y-axis, and here we have the z-axis. So this is the positive x-axis here, this is the positive y-axis here, and this is the positive z-axis. And we can see here that we start at this point when t is equal to 0. We get b0. X is b and y is 0. And the circle that would be traced by these 5 points would be here. This would be the circle that's traced by these 5 points. And if you extend that circle above the xy plane and below the xy plane, you get a cylinder. And it is on that cylinder that you get this space curve, which I will now show in red. So this is the space curve that you get on the cylinder. Traced from t is equal to 0 to t is equal to 2 pi. So how do you know where on the cylinder you will have a point? You have to look at the third component, which is given right here. And if you evaluate the third component at each of these values of t, now in addition to the ordered pairs that we have here for x and y, we will now have ordered triples with a z coordinate. So when time is equal to 0, looking at z of t is equal to the square root of 1 minus b squared times t. When time is equal to 0, z would be 0. And that would give you this point, which would be on the xy plane. And if you evaluate the component function for z at the other values of t that I've shown here, you will get these z coordinates, which you will fill in here. And of course, b is just a constant that gives you the radius of the circle in the xy plane. So the square root of 1 minus b squared is just a constant that depends on the value of b, whatever b may be. You just multiply the square root of 1 minus b squared by t. So if t values are positive, you'll get positive z coordinates. If t values are negative, you'll get negative z coordinates, and so on. So what happens as t increases? You just have points that are more and more and more above the xy plane. So the spiral, as you are going around the cylinder, is also climbing for that reason. So this is just for your information. You don't really need to know this to be able to just find the arc length of this one turn of the helix. All you need to do is apply this formula for the vector valued function that we have describing our helix. So I will start as follows. The arc length is given by the definite integral from t is equal to 0 to t is equal to 2 pi. And the integrand will be the square root of, we're integrating with respect to t, and in the radicand I need to find the derivative of each of my 3 component functions, and then I have to square each of those derivatives. So the derivative of b times cosine of t with respect to t would be, the derivative of cosine is negative sine, so I'll have negative b times sine of t, and of course I have to square that. The derivative of b times sine of t with respect to t, b is just a constant, so the derivative of sine is cosine, so I'll have b times cosine of t, and I'll have to square that. And for the z component, remember, the square root of 1 minus b squared is just a constant. The variable is t, so the derivative of a constant times t is just that constant. So I'll have plus the square root of 1 minus b squared, and of course I have to square it as indicated by my integration formula for arc length. Once you've done the setup, you just need to simplify the integrand, and here's how you would do that. So when you square negative b times sine of t, you'll get b squared times sine squared t. When you square b times cosine of t, you get b squared times cosine squared t. And when you square the square root of 1 minus b squared, you get 1 minus b squared. So the next step is to further simplify the integrand. And one thing that you can see right here is that these two terms in the radicand, they have a common factor of b squared. So I can factor out b squared. I'll be left with sine squared t plus cosine squared t plus 1 minus b squared dt. And one thing that I know is sine squared t plus cosine squared t is 1 by the Pythagorean identity, so I can replace that with 1. And when I do that, I just get b squared times 1. And you can look here and see that in the radicand, which is really spaced out, but that's not necessary anymore. But the point that I want to make is you have b squared minus b squared, which is 0. So you just have 1 for the radicand. And the integrand is just the square root of 1. So I just have 1 for my integrand. That's super easy to integrate with respect to t. The antiderivative would be just t, because the derivative of t with respect to t is 1. And now you will just integrate, well, we've already integrated. So you will evaluate your antiderivative at the upper limit of integration 2 pi, and you get 2 pi, and evaluate the antiderivative at the lower limit of integration 0, and you get 0. So the length of the arc, or the length of this helix, is going to be 2 pi units. So today we looked at finding arc length of a plane or a space curve described by a vector valued function, and the main thing for you to walk away with from this lesson is that this is done the same way where you were finding arc length of arcs described by parametric equations.